Hi everyone, and welcome to the first online lecture of Biomaterials 1. This lecture is about metals and ceramics. I'm Professor Kara Spiller, and I'd like to thank my excellent TAs for coming today to sit behind the camera so I don't feel weird talking to a camera, and also to ask any questions that might arise that are clarification or just further elaboration or anything. So thank you. Okay, so anytime that we're thinking about biomaterials and their design, I think that it's useful to think about this outline for biomaterials research. So, of course, you need to be familiar with the common uses of the materials. It's really important to think about the advantages and disadvantages of the biomaterials. And, of course, for something that's constantly evolving, like biomaterials research, you're going to have considerable disadvantages that we're still working to overcome. The mechanisms of failure are really important and very helpful for determining how to better design and improve a biomaterial for the next time. And interactions with the body is what makes the field of biomaterials extremely unique within materials engineering, because that is 9 times out of the 10 the actual mechanism of failure is that the interaction with the body was not favorable. So it's important to understand the most common mechanisms that the body interacts with these implants. So let's start with metals. Metals are extremely common in orthopedic implants and also in cardiovascular implants. In fact, 4 out of the 10 most frequent orthopedic procedures involve metals. It's a big market, and metals are also really common in surgical instruments, which is considered by the FDA to be a biomaterial. Although today we're going to be focusing mainly on implantable metals. So when I think about metals in biomaterials, my mind immediately goes to the total knee replacement or the total hip replacement prosthesis. So in this design, you have a piece of metal on the top, but the tibial surface is removed and a piece of metal fits in there and it interfaces really tightly with the bone. And then the femoral surface is also modified with metal. And sometimes you might have a ceramic coating on there too, and then there's a plastic spacer in between. And so you can already see that there's a lot of different forces that are acting on a metal like this. So the biggest one that I see immediately is that you have interaction with the bone. It needs to interface really well with the bone in order to have appropriate load transfer. You have extremely high compressive forces in a joint like the knee. It can withstand up to 10 times body weight. And you also have considerable friction and wear that comes in an articulating joint like this. So it's really important to understand how these materials actually behave in all of those scenarios. Since a lot of the students in this class are seniors that will be graduating soon, it's important to be aware of the major manufacturers of metal implants. So if this is something that you're interested in, you should keep an eye out for the main companies. It's a huge market and there's a lot of positions available. The second most common use of metals in biomaterials, in implantable biomaterials, are cardiovascular applications. So metal stents have been around for a really long time, and the way that they work is you have an occluded artery due to atherosclerotic plaque building up, and that actually impedes flow through the artery. So what you do is you can have a collapsed stent, and you insert it into the artery, and then you put a balloon inside and inflate the balloon to expand the stent to its correct size. And that actually physically holds open the artery. And that works very successfully, but you can see right away that you have a lot of different properties that you need to consider when you're designing a metal for a stent as opposed to a orthopedic device. So the forces that you have here are flow. You have a lot of interactions with the blood, so you have to be really aware of any anti-thrombogenic properties that you want to have, or maybe it has a lot of cells of the inflammatory system flowing through there, so if it elicits an inflammatory response, that's really going to be a problem, and more so than it would be in an orthopedic implant. So it's really good to understand how these materials interact with the body in order to design them. If cardiovascular stents is something that you're interested in, this is also a really big market, $6.4 billion globally, 37% of that is in the US. There's many more companies than Johnson & Johnson and Boston Scientific, but I just listed the 2 main ones. Okay, so why do we use metals in biomaterials? They have high tensile yield and fatigue strengths, which means that they won't break under the loads that you need, that you're going to be seeing in that in the desired application. So you would that's why you would use a metal if it's going to be withstanding a lot of forces. You can control the properties of the metal based on the processing methods, and a lot of times you will read that metals have low reactivity in the body. And I have an asterisk there because since my current research is in the inflammatory response to biomaterials, I always hesitate to use terms like low reactivity or biocompatible as an advantage of something, or even just something as vague as biocompatible, because in different applications, you're going to want a different level of reactivity. So I mentioned with the stent, you have a lot of inflammatory cells flowing through there, so that's something that you want to be less reactive. You don't want the cells to be able to activate in response to this metal that's in the blood. But for something like an orthopedic implant, if it's just articulating in synovial fluid with another biomaterial, another foreign body, it has a lot less access to the blood and a lot less to the inflammatory response, so you can actually have some more reactivity in the body than you could in a stent. However, if it's going to be trying to integrate with the bone, like the stem of a prosthesis, then that should interact very favorably with the body. So not only can it not activate any immune cells, it should probably make the bone-forming cells want to form bone. So you want to be careful. So when you're making a presentation, don't just say low reactivity and act like that's a good thing. Okay? And when you see that in a textbook, I want you to think about that. Okay, so everybody knows what metals are, so I'm not going to go over the basics of them. It's a crystalline structure with multiple grains. Basically, you have metal ions that are surrounded by an electron cloud, and the whole thing is held together by electrostatic interactions. The grain boundaries are really important for propagation of failure, but I know you all learned this in previous courses, so refer back to your notes from those courses for more detail. Okay, so how do you make a metal implant? Metals are found in the Earth's crust, so the first thing is to mine them. So we get them from rock and sand, and you can physically separate them and go through chemical treatments. Then there's a whole lot of chemical and heat treatments that are involved in increasing the purity and also adding any alloying materials that will drastically change the properties. So these are some of the things that you can do if you need to change the actual material properties of your metal for a specific application. So we're not going to get into too much of that, but that's the basic flow. So the most common materials that are used in orthopedic applications, the most common metals, are stainless steel, cobalt-based alloys, and titanium. So stainless steel is primarily iron with a significant amount of chromium. Cobalt is mostly cobalt, also a significant amount of chromium. And titanium is actually often used in a pure form. So in terms of advantages of all of the metals is going to be strength, and that it takes a lot to make them break. And a lot of times they're not too difficult to manufacture, especially for stainless steel and titanium, because they're ductile and malleable, especially at high temperatures, so you can forge them into the shape of the implant that you want. There's some disadvantages, especially for stainless steel and cobalt-based alloys, and that's that they have extremely high moduli of elasticity, extremely high Young's moduli compared to cortical bone. So we'll get into more details about that a little bit later, but the underlying problem is basically just that it's a mismatch of mechanical properties with bone. Titanium has a lot lower modulus than the other two, but it's actually still higher than cortical bone, so you still have a mismatch of properties. And some of the titanium has a little bit better corrosion resistance, which we'll get into later. But yeah, these are just some of the things that you need to consider: resistance to wear, stuff like that. Okay, so we talked about these mechanical properties as being one of the most important things you have to consider initially in designing a material, and also in why it failed. So just to quickly review, stress and strain. Stress is the force divided by the area. Strain is change in distance relative to its starting point. So if you have a stress strain curve for material A and a stress strain curve for material B, because it takes more stress to get the same strain for something like material A, so that has a higher slope, that is a stiffer material, so that has a higher modulus of elasticity. And if it's a straight line like that, it's elastic, and that means that it can respond, it can go back to its original shape after applying the force. This is a stress strain curve for a typical ductile metal. So you might, for low strain values, you probably have some elastic behavior, and you can take the slope of that in order to get the Young's modulus, which you can think of as stiffness. But at a certain point, it hits the yield point. And at that is the point that after which it starts having plastic deformation, so it won't fully return to its original shape after you remove the force. It'll start necking if you're pulling it apart. If you're compressing, it's going to expand the other way, and then eventually it'll break. So there's some important some important spots here that you need to know about. Yield strength is important because after that it starts deforming. Ultimate strength is the highest stress that you can apply to it, and then the fracture stress is of course really important so that you know where it's going to break. So that's what a stress strain curve looks like if you're just going to pull apart a standard sample in tension. But in reality, for an orthopedic implant or for any implant, it's a much more complex shape, and it's not just a uniform stress and strain in the material. You have a whole distribution of stresses depending on the shape of the material and its composition. So modeling of the stresses can be really important to see if there are parts where stress could be concentrated, which would lead to failure of the metal before you might realize that would happen. So it's really important to do some modeling of the shape of the biomaterial in order to understand where the stresses might concentrate. Okay, so just to go over some definitions, because as a biomaterials engineer, one of my biggest pet peeves is when people misuse terms and they say, oh, this is the best, this is a good material because it's so strong, but what they mean is that it's so stiff. That's just really frustrating because we need to be actually specific about what properties you're talking about so that you can actually have a scientific conversation about it. So don't misuse these terms. Elastic modulus you can use with stiffness. It's the slope of the linear portion of the curve, as I just said. I went through these already, so I won't repeat them. Toughness is something that is really useful for implants. That is the energy needed to break the material, and you can calculate it as the area under the curve to fracture. So if you do the curve, if you keep applying stress and it keeps straining until break, you can take the area under the curve and call that toughness. So that's really useful to know. Some more definitions. Ductility just means metals are ductile and malleable, which means that you can deform them under tension or compression respectively, which is useful because if you're trying to forge it into a certain shape, you need to be able to do that. Poisson's ratio is useful, especially for a biomaterial that if it's going to be changing too much inside the body, then you need to be aware of that, about how it's going to change. So that's a measure of how much it contracts if you pull it and how much it expands if you push it. The shear modulus is the response to strains that are parallel to the surface, and that's going to be important for an articulating joint or for when something has a flowing force going past it. So it's important to know those terms. Okay, so what are the important mechanisms of failure of metals? The way that biomaterials engineers study mechanisms of failure is by retrieving implants that have been that needed to be removed from bodies for whatever reason, either failure or it's a cadaver body. So we have a Drexel Implant Research Center here that is very renowned, and basically you can just retrieve the material and analyze it. And what you're looking for is, was there a specific vulnerability in the prosthesis that's common among all the similar prostheses in a similar group? Or was there something specific to the patient population? So you basically want to get a lot of data and try to find patterns to see what made that prosthesis fail, and is it something you can use to redesign the next iteration. And it's also really important because it influences product liability litigation, which in our litigious society is, of course, an important thing to think about, and it also can help you maybe change the patient cohort that you're going to treat with a particular prosthesis. So this is a really useful field. One thing that is really important in metals especially, but in all materials, is fatigue. So that's the failure under cyclic stress. So nothing in your body is just going to be exhibited to a simple compressive force or a simple tensile force. You're going to have cycles of stress and strain, and that's because you're walking around, you're standing, your heart is pumping at a sinusoidal rate. And so the way that I like to think about progressive fracture that comes from fatigue is like when you bend a paper clip back and forth, and originally it's fine, but then eventually it breaks because the stress got concentrated where you were applying the cyclic stress and strain until it just broke. Okay, so this can be counterintuitive sometimes because the fatigue, the ultimate fatigue limit can actually be less than the yield strength or the fracture strength. So you can't just stop there. You need to do fatigue testing before you can ever implant a material in a body. And it's causes up to 90% mechanical engineering failures, and I don't have a statistic on how it affects biomaterial failures, but I imagine it's pretty high. A famous case of failure due to metal fatigue was in the tilting disc heart valves in the 90s. So this was a valve that went inside the heart, and the valve actually goes back and forth like this, and it's welded on the two edges, anchoring the struts that make it go back and forth. And so this was designed fairly well. I think so. It's a cobalt-based alloy. It was designed very well, but what they didn't count on was young people exercising more than older people. And so, of course, your cardiac output goes up when you exercise. The valve closing velocities went up a lot higher than they realized, and the fatigue properties were different. And so it actually had a very strong inverse correlation of failure with age. So it failed a lot more in younger people than in older people, which is oftentimes opposite for biomaterials. So, so the point here is that you can't just test simple properties of materials. You need to understand the fatigue properties as well. Okay. Friction and wear is something else that's extremely important, especially in orthopedics where you have articulating joints. This will result in the generation of wear particles sometimes if you have a material that's not sufficiently resistant to wear. And then these particles can go on and activate the immune response to have an adverse reaction even way later than the implant, 20 years later, because if the wear finally starts happening and these particles come and activate the immune response. We're going to go into that in a lot more detail later in this course and in the next sequence of this course. But suffice it to say that wear is an important property that you need to understand. So there's metal and metal hip replacements that are still really popular, and ways that they have been examined is the elevated, or have been, that they realize it was happening in a patient is that there's elevated levels of cobalt and chromium in the blood and urine. And so they're still doing toxicological testing on the effects of these metal ions on the body, but you can imagine if that gets really high that would have adverse systemic effects. I thought it was interesting that there was one paper in 2001 that showed that they actually decreased wear and increased the resistance to wear by just changing the diameter of the femoral head. So this is in a hip replacement where you have a cup and the ball articulating inside the cup. And just by increasing the diameter, it decreased the wear because it changed the tribological properties. It changed the lubrication and how the lubrication happened. And so the lubrication actually got better just by changing the shape of the material. So that's like a really important area of biomaterials. Sometimes you don't need to actually go back and change the whole properties of the material. You just need to redesign the shape. So that's why it's really useful to understand the biomechanics of what you're applying to. So resistance to wear of metals is related to hardness, strength, ductility, a lot of things. There's some coatings or some surface treatments that you can do to increase the resistance to wear. Like nitriding, where you you basically shoot a high energy beam of nitrogen ions onto the surface, and that increases the hardness, or you can coat with a thin diamond film. But what's become the most effective way of doing it is just coating with a ceramic, which we're going to talk about in a couple slides, but ceramics are known to have better resistance to wear than metals. Okay. Another way that metals often fail is through electrochemical corrosion. So that is the electrochemical degradation of a material through interactions with its environment. So these are some of the concentration of the ions that you have in blood plasma and extracellular fluid. And as you might expect, they're extremely high. And of course that changes depending on where the material is going to be implanted. And you also have a lot of proteins in the blood and plasma, and you have a lot of cells there. So all of these things are going to really, they're going to interact with the metal and degrade it through electrochemical interactions. So how that happens is that you have these metal ions that are oxidized in an aqueous environment, and because of the necessity for equilibrium of the rates of the anodic and cathodic reactions, this is effectively a continuous process, because as soon as the electrons get released, they go and they reduce other ions in the vicinity, or they reduce proteins, or and then they're cleared by the body. So if you keep clearing the electrons, the anodic reaction keeps happening, and so it effectively ensures continued erosion. And this is also why variations in the local environment will affect corrosion rates. So a lot of times you see people testing biomaterials in simulated body fluid, and this is why you need to test that as opposed to just using like a saline solution, because it changes. And it's also why you need to really consider where you're implanting the material. So you can predict whether or not a metal will be degraded, how quickly it will be degraded based on its electronegativity. Its electrochemical potential. And the metals at the top of the electrochemical series are referred to as the noble metals, and they are very resistant to corrosion in the body. So the earliest metal biomaterials were made with gold and platinum and silver. But what I want to point out is that some of the materials that are on the bottom of this list, like chromium, aluminum, and titanium, we already saw that they're really important components in metal implants. So how does that work? When you have extremely reactive metals like titanium, aluminum, and chromium, they react so quickly with oxygen upon exposure to the atmosphere that they form an oxide layer on the surface of the material that actually is attached to that material and is impervious and protects the underlying material from further corrosion. So it's sort of like the fact that it is such a corrosion susceptible material actually makes it less susceptible. This layer can be broken down by a lot of things like wear and mechanical forces, but this is why chromium is so important in the stainless steel and cobalt-based alloys, and that's why titanium is a good metal for biomaterials. Okay, so I alluded to this earlier, but an important mechanism of failure of metal implants, especially for orthopedics, is stress shielding. And so that is when the stem that goes into the bone is so much stiffer than the surrounding bone that it actually doesn't transfer the load to the bone, and then the bone, which it requires mechanical loading for proper homeostasis, that actually dies. And so you have implant loosening as the bone around the implant dies, and that could happen a lot later, and that's actually what causes a lot of failure. So if we look at the Young's modulus of the common metals in orthopedic implants, bone is at the top there. It has a Young's modulus of 5 to 23 gigapascals, and that's actually really high, but titanium, all of these ones are a lot higher. Titanium is a lot lower than cobalt alloys and stainless steel, but it's still higher. And so that's why you can have stress shielding for any of these. And a really active area of research right now is trying to redesign biomaterials so that you have less stress shielding? Can you design some sort of interface like a bone cement that transfers the load better from the implant to the bone? And also just developing novel materials that have mechanical properties that match that of bone. Those would both solve those problems. Osseointegration is also used to, for biological fixation of the implant into the bone, and is also helpful to avoid stress shielding because it's like a natural interface between the implant and the bone to transfer the loads. So osseointegration is when the bone actually grows into the implant. So for that to happen, the implant needs to be porous, at least on the outside, and that actually fixes the bone into place. So originally, when that was developed, materials that would increase osseointegration, it was sort of empirical. They just found that when they had used rougher materials, they actually supported better osseointegration. And then later it was found that that's probably because surface roughness enhances osteoblast differentiation in vitro. So it actually increases the osteogenic capacity of bone. And then porosity, I think that's kind of obvious to see why that would increase osseointegration, because the bone can actually grow into the pores and anchor it in place. A lot of studies have been done on that too, though, so that you can, we now know that the pore size has to be around 150 microns or larger so that the bone will actually grow in and so that blood vessels will grow in. So ways you can increase surface roughness is high temperature sintering of alloy beads onto the surface of the metal, or just etching or flame spraying of the metal powder onto the surface. And ways to add a porous layer are you can add a metal fiber layer, which is shown in the picture here, or you can just add a porous ceramic. So that brings me to my discussion of ceramics. So ceramics go hand in hand with metals because for orthopedic implants, they are used together. So ceramics contain metallic ions. They're compounds of metallic and non-metallic ions, usually oxygen. So we talked about in metal implants where you have that oxide layer, that's sort of like a ceramic layer that's protecting it from corrosion. So ceramics are naturally extremely corrosion resistant, which is why they make great coatings for metals. You have natural ceramics that are found in bone, teeth, and shells, and so nature has evolved to use ceramics, and so you can, whenever that happens, you know it's a useful material. But that's mineralized protein, so it has slightly different properties than really different properties than the ceramics that we can make synthetically, and that's part of the problem, that we haven't been able to actually recapitulate the mechanical properties of natural ceramics. But these are primarily used in dentistry and orthopedic applications. So advantages and disadvantages, they're still strong and tough in compression, so they're unlikely to fracture under the loads that you need them in orthopedic implants. They have much lower moduli of elasticity than stainless steel or cobalt, so that's better for the stress shielding aspect. So if you can use as an interface, that might transfer the load a little bit better, although it's still higher than bone, in some cases at least. They have really good wear resistance, and so that's probably one of the best reasons for using a ceramic in an articulating joint. And they also can be processed to be porous, so then that would allow some osseointegration. They're biomimetic, because we just talked about the ceramics that are found in nature. They can be biodegradable and bioactive, so that means they can even, the bioactive in this sense, which is overused a lot too, bioactive in this sense means that it actually chemically bonds to the bone. And we'll talk about that a little bit later too. Some disadvantages is they're brittle. They have low toughness and tension, so if you have a complex biomaterial that has to withstand both tension and compression, they may not be the best choice. And sometimes the resorption rates can be low, but mostly it's just that you have to try to match the resorption rate, if it is resorbable, to the rate that new tissue grows, and that's not easy. So bioceramics are often used as bone substitutes in non-load-bearing applications, or at least in load-bearing applications that are not as much as like an articulating joint. So you wouldn't use it for the entire knee prosthesis, but you would use it to fill in a defect in a long bone, or definitely a maxillofacial bone. The common implant ceramics and biomaterials are alumina, zirconia, and calcium phosphates. And these are generally those, so alumina and zirconia are those metals with oxygen, and then calcium phosphate is as it sounds. So I talked a little bit earlier about how bone is a natural ceramic, and I guess what we're talking about here is that we're trying to mimic bone in order to replace bone, right? So it's helpful to look at the ultrastructure of bone. What you have mineralized proteins, basically, and so while ceramics that we might make in the lab are really brittle, bone is not that brittle because it's held together by a collagen network that's really strong in tension, and that can also swell with water, and so all of this leads to a decrease in the brittleness. So if we could figure out how to mineralize collagen matrices like bone is, then we could make a better bone, but we haven't yet. So the market data for ceramics in orthopedic products is it's increasing every year. This is a rapidly increasing field, so this would be a good one to go into. This is actually just even a portion of it, this graph here, but I thought it was good. And there's an excellent market analysis, I think from 2008 on the link that was there. But these are some of the major companies that are manufacturing ceramic bone substitutes. An example is a bone void filler that is produced by Integra Life Sciences, and so they have granules of beta-tricalcium phosphate, and they just kind of package them as granules, and you would just pack them into a bone defect. And what they're showing in this image is that they soak up blood, and they say that that's good because there's stem cells in the blood and other useful things. That's something that is an active area of research too, is the interaction with the blood, and can you actually use that to make it more bioactive? So I'm not sure that's quite known yet. Okay, there's different types of ceramics based on their microstructure, and these are basically they're all different because of their processing methods and the heat methods that were used to manufacture them. So we're not going to go through all of these, but basically glass is an amorphous solid, so you heat up the ceramic, and then when you cool it, it doesn't form a crystalline structure, so that's why it's a glass. And then you can also have ceramics that are part glass and part crystalline, and that there's different phases or different structures. So their microstructure is a lot more complex than metals. Their microstructure is mostly ionic bonding based on the differences in electronegativities of their metallic ions and the other, whatever else they're with it, whether it's a phosphate ion or an oxygen ion. And so you can actually predict how ionic the structure is based on how far apart from they are on the electronegative table. So that changes their microstructure, which is going to change their properties, so that might be a way to control the properties. Bioglass is a really interesting type of ceramic for biomaterial applications because it actually forms a covalent interface with bone, which I think is, it's a bioactive hydroxyapatite layer, so it's a ceramic layer in there. But it actually bonds to bone, and it was found empirically that the best formulation is 45% weight silica and a 5-to-1 ratio of calcium oxide and pentaoxide, or whatever that is, phosphorus pentoxide. And so that's really useful because it can actually bond to bone and form a good interface there, which is important for load transfer. And it gradually dissolves, so that's nice too, that it has the potential to be replaced with normal bone. Porous ceramics are another really active area of research where the idea is to try to control the pore size and the structure to maximize bony ingrowth. So porous ceramics are often used as the coating of metallic implants in order to maximize bony ingrowth, and they're prepared by just sintering a ceramic in a mold that you later burn out in heat processing treatments or just in gas foaming. And ceramics can dissolve over time. The rate of dissolution depends on their properties, of course, and how strong the bonds are between their ions, and also how reactive they are with the with the ions present in the body. So that's another thing that you can manipulate in order to match your application. You know, if it's not degrading fast enough and the bone isn't able to effectively replace it, then you can change the properties to make it degrade faster, and vice versa. Okay, so what are the mechanical properties of ceramics? Again, this is something that really varies depending on its composition and its structure. The porosity, of course, is going to be inversely relational to mechanical properties. So, but just as a general rule, you have cortical bone, which is has a much lower Young's modulus than alumina and the calcium phosphates. Bioglass ceramics are close to the Young's modulus, but that's just one aspect of their mechanical properties that's listed here, and you would need to analyze it, of course, in a whole range of mechanical properties to make sure that it's a good match. So when we're talking about ceramics, I think that the interactions that ceramics have with bone are really interesting. And just looking at my notes here. So there's some definitions. These are some buzzwords that a lot of times you hear in biomaterials research, so it's helpful to know what people are talking about, although I've heard them all used interchangeably, and so I don't think that's really, but you should know what they actually mean. So if a material is osteoconductive, that means that it facilitates blood vessel and bone ingrowth into the scaffold. That's very similar to osteoinductive in that an osteoinductive scaffold stimulates surrounding mesenchymal stem cells or even really just bone-forming cells to infiltrate the graft and to differentiate into bone-forming cells. So you can see how they're very similar. Osteogenic is more specific, and that means that it actually promotes the osteogenesis of MSCs within the graft. So you usually only hear osteogenic reserved for scaffolds that either contain MSCs when you implant it, so more of a tissue engineering approach if you seed it with stem cells, or if it can actively recruit stem cells and then release some sort of bioactive factor in order to make it to make them differentiate into bone cells. So I took this from Integra's website. They showed osteogenesis in vitro on their material. I don't remember which one this was, but pretty cool pictures that they showed that osteogenic cells, they say, grew on it and differentiated into osteoblasts over time. So I think they're cool pictures, and this is a great study that a lot of people do, but I think it's important to remember too that how many MSCs are actually present when you're implanting into bone, and there's actually a significant number in bone marrow, but it's still not that many. So if this study, if they put in 1 million MSCs onto the bone and then they differentiate into MSCs, it's definitely good to know, but that doesn't mean that it's going to be effectively osteogenic in vivo. So definitely a good experiment to do, but it's just one of many that you need to do when evaluating a biomaterial. Okay, so bone graft substitutes that are scaffolds, there's a lot that this table kind of lists some that are osteoconductive and inductive. For osteogenesis, you can see that they say that you need to have a bone marrow aspirate or MSCs involved. So there's that. In terms of scaffolds, this is sort of helpful to talk about what kind of scaffolds have the different properties. So the gold standard of care for replacing bone that you need to remove because of trauma or cancer or something is just an autograft. So if you could take bone from another part of your body and replace that part, that's what you want to do. That works the best. It's osteoconductive, inductive, and osteogenic. If you can't do that, of course, you can't do that very often because you need bones in the other parts of your body. You can use an allograft where you can take a bone from another person, so like a cadaver, and that's used a lot too, and that works really well too. It doesn't work perfectly, which is why bone tissue engineering exists, but that's for another course. And then you can also use demineralized matrix, which is what DBM is, demineralized bone matrix, and that's often used from a xenograft from an animal product. And then there's a lot of scaffolds based on ceramics and composites between natural materials and polymers and ceramics. And they have their own advantages and disadvantages that you can, that are, there's so many different types. You can look into that later. Okay. We're nearing the end here. Don't worry. So there's 4 different types of responses, of tissue response to implants. And this is, you can probably think about this for a lot of materials, but this is specific to ceramics and bone. So the first response is when if you implant, it's called nearly inert. It's the type 1 response. And when you implant it into the body, or into the bone, it doesn't really interact with the bone. And these are, if you implant it into the bone or a soft tissue, it's probably going to be encapsulated by a fibrous capsule by the immune system. A type 2 material is porous ingrowth, so that's when you have osteointegration due to pores. That's pretty self-explanatory. Type 3, bioactive, that's like the bioglass, that the material actually chemically bonds to bone, and that's a pretty tight interface. And type 4, resorbable, that's where hopefully the bone replaces the ceramic that degrades over time. So just want to go over each one. Type 1, nearly inert, there can be some movement between the implant and the material because it's not bonded, which can definitely be that would be the form of failure if you tried to use this type of material in an actual implantation. However, if you don't want it to interact with the body, like if you want it to be articulating in a hip joint or in a knee joint, then you don't really need it to attach to anything, but what you really want is great resistance to wear. So if you have a very dense, non-porous, nearly inert ceramic that's very resistant to wear, that's going to work great in a hip replacement joint or in a knee replacement. Okay? And so an example of that is alumina. So a lot of times that is the top of the femoral head and the inside of the cup in a hip replacement. So that's why you would use a type 1 material there. Type 2, porous ingrowth, you have biological fixation. We kind of talked about this in a couple different ways earlier. A disadvantage of this is that you might have some micromotion in between. Now you have like an extremely complex interface with the tissue because the bone goes into the pores and it could move around within a pore. So now you actually have a lot more interface to worry about, and so if it doesn't fix it very well, and if you do have micromotion, that could actually lead to implant loosening too. So if the porous ingrowth is not good, then this is going to fail. So this is an example of this is when you coat like a femoral stem in a knee replacement. Type 3, bioactive. This is like the bioglass that we talked about. So that's when it actually bonds to the bone, and that works well, but it's not perfect either. And so this is something that you would definitely want to think about, and it's a good coating too, but also not perfect. So you need to think about that. And then type 4, resorbable, the resorbable response, that's where the material degrades over time and it's replaced by bone. This is an extremely active area of biomaterials and tissue engineering research because it would be awesome if you could get new bone to replace the material over time. That's what everyone's trying to do. But there's some complications that make this a really challenging approach, and that is that first of all, they need to have some initial properties that allow them to withstand the loads that are going to be on them, especially in something like a knee joint or a hip joint. And then as they're degrading, they need to transfer some of that responsibility of the load bearing to the new bone, but still maintain it, and the interface needs to maintain that sort of integrity too. And then also you have to match the rate of resorptions to the new bone that's forming, or you would have some gaps there, which of course is going to be a huge potential mechanism of failure. So a lot of what people are trying to do is only use ceramics that are degraded actively by the bone. So maybe like an osteoclast in the bone will degrade the ceramics, and that so you don't actually have any degradation unless there's cells forming there. So that is a really cool area, but it's still very much in the research phases. Okay, finally, there's a new material out by Smith and Nephew called Oxinium, or it's a new system, I guess, where it's a smooth transition from a ceramic on the surface of a femoral head to the metal in the stem that goes into the bone. And so I just read an article on this which makes it sound really promising, and that it's scratch resistant, and there's less wear, a lot less wear on the articulating surface, so it should have, one of the problems that we're going to talk about in later classes and in the next sequence of this course is that the wear that's produced by polyethylene spacers is what is actually causing the failure of the orthopedic implants. So since this reduces the wear of the polyethylene, then that would reduce failure of the implant. And it has a much lower modulus than stainless steel or cobalt, so you have less stress shielding. Of course, since it's transitioning to metal, that's not really as much of a problem since it's only on the articulating surface anyway, so it's actually the metal that you want to talk about as having a better interface with bone. So, in summary, we talked about the uses that you have for metals and ceramics and biomaterials, their advantages and disadvantages, which I understand are extremely site-specific and material-specific and even like situation-specific. So whenever you're designing a biomaterial for a specific application, you definitely need to be aware of what sort of loads are going to be on it in a general sense, but also what sort of environment that you're placing it in and what's going to be in the environment and what can lead to its possible failure mechanisms, which we talked about. And so interactions with the body are probably the most important thing that you need to consider when you're designing a new biomaterial. Okay, that's it. Thank you.